This video will cover the Friedel-Crafts Acylation reaction. This is similar to the Friedel-Crafts Alkylation reaction, but instead of an alkyl group, it adds an acyl group. And instead of using an alkyl chloride as our electrophile, we use an acid chloride. In the Friedel-Crafts acylation reaction, benzene, or another aromatic molecule, is treated with an acid chloride. In the presence of a Lewis acid, aluminum chloride, to form the acylated benzene. Typically, to get the final acylated product, we have to then treat it with water, which removes the aluminum trichloride complex with the carbonyl. Notice that in this reaction, just like in the Friedel-Crafts alkylation, the electrophile is carbon, and therefore we form a new carbon-carbon bond in the Friedel-Crafts acylation reaction. The electrophile for this reaction is formed by treating the acid chloride with the Lewis acid, aluminum trichloride. The acid chloride donates electrons to the Lewis acid to form a complex. Next, the chloride leaves the acyl group to form AlCl4- and the acylium ion, which is resonance stabilized. Because this carbocation is resonance stabilized, there is little chance of rearrangement, because it is unlikely that a more stable carbocation can be accessed through such a rearrangement. Now let's look at the electrophilic aromatic substitution mechanism with the acylium ion acting as the electrophile. Again, note that this will be an abbreviated mechanism. Make sure that you can write out the complete version with all of the resonance structures for the sigma complex. Once the electrophile is formed, as shown in the previous mechanism, the benzene ring attacks at the positively charged carbon. This generates the resonance-stabilized sigma complex intermediate. In the next step, the sigma complex is deprotonated by the aluminum tetrachloride ion. This generates the acylated benzene as well as hydrochloric acid and aluminum trichloride. The aluminum trichloride is still a good Lewis acid and forms a complex with the carbonyl oxygen. This complex remains until the water wash, which removes the aluminum trichloride to give us our product. Next, let's consider the benefits and limitations of the Friedel-Crafts acylation reaction. In comparing Friedel-Crafts acylation and alkylation, we learn that the acylation still does not work with strongly deactivating systems, just like the alkylation reaction. So for example, we cannot perform a Friedel-Crafts acylation reaction on nitrobenzene. There are some benefits, though, when comparing Friedel-Crafts acylation and Friedel-Crafts alkylation. The first is that no carbocation rearrangements will occur because the acylium ion is resonance stabilized. Therefore, we can use Friedel-Crafts acylation to make alkyl benzenes that cannot be made through Friedel-Crafts alkylation. Let's look at an example. If we would like to make propylbenzene from benzene, we will not be able to carry this out with a Friedel-Crafts alkylation. If we were to treat benzene with propyl chloride in the presence of aluminum trichloride, we would see rearrangement of the carbocation to form isopropyl benzene due to the increased stability of the isopropyl carbocation compared to the propyl cation. However, we can use Friedel-Crafts acylation to make this particular alkylated benzene. If we treat benzene with a corresponding acid chloride in the presence of aluminum trichloride followed by water, we will produce the following acylated benzene. We can then use the Clemmensen reduction to reduce this down to the desired alkyl benzene product, with no threat of rearrangement. we get only the desired product. Another benefit to the Friedel-Crafts acylation when compared to the alkylation is that the products of a Friedel-Crafts acylation are deactivated compared to the reactants, so we don't have any problem with over-acylation. Remember that this is not true for the Friedel-Crafts alkylation. Alkylbenzene is more active in the electrophilic aromatic substitution reaction, where an acylated benzene is less reactive. One final thing to remember with the Friedel-Crafts acylation reaction is that the electrophile for this reaction is very bulky. Remember that the electrophile is a complex of the acylium ion and the aluminum tetrachloride. Therefore, we will typically see that para substitution is favored over ortho substitution. This effect becomes more pronounced as the initial substitution on the benzene is more bulky.